So everyone got the midterm solutions?
Yes.
Good. So they are written in a variety of handwritings because some of the problems I had solved in some other context, so I didn't want to rewrite it again. Problem 4, I did all over again. And that's a problem that you should all look at. It was actually I think it was my favorite problem on the midterm. It was not that hard, but it was easy to get confused in. One of the key takeaway points from that problem was that if you have a crystal made up of atoms connected with harmonic springs, so let's say it's a three-dimensional crystal or whatever, and things are connected through harmonic springs, so everything is F is equal to minus kx. Then as you increase the temperature, this crystal will expand more and more. So the atoms on an average will get further and further as you increase the temperature. Things will try to oscillate more, but they won't oscillate just in one direction. They will also oscillate in this other direction, right? They will compress as much as they expand. So the funny thing about a harmonic crystal is that while the fluctuations increase as a function of time, the mean position stays the same. What it really means is that a harmonic crystal, so we are talking about midterm problem number 4. So a harmonic crystal never expands. It fluctuates more and more, but if you think about the coefficient of thermal expansion, alpha, that will be 0. And this is a very interesting point. So in order for thermal expansion to happen, we need n harmonic interactions for thermal expansion to happen. And this really makes the problem easy because now you know that the average displacement in any direction is going to be 0. So all of these are going to be 0. However, this does not mean that x square is going to be 0. Those things will be different, and that's what you had to calculate. And so if you have any more questions about the midterm solutions, either of the office hours, 6 of you responded to the office hours. And there were 2 people who could not make Monday. There were 2 people who could not make other days. So I have done 2 office hours, and they will be just half an hour each. It doesn't mean that if the discussion is running longer than half an hour, I will just stop the meeting. I mean, but try to be, so we will split it that way. Okay, so any questions about last class? No questions? Okay, so let's try to see what we had derived. So we had derived an interesting relation, and let's try to get a bit of intuition into this. This shows why G of R is called potential of, why is it called potential of mean force? So the relation we had derived was if we had a bunch of particles just moving around. So we are interested in an n particle system at some temperature T, and with some interaction potential u r of n, while this r of n here, as I described in our first Zoom lecture, is a collective way of writing R1, R2, Rn. So the superscript means all capital N particles are considered at the same time. So we have this some generic potential. And the interesting relation that we derived was that if we fix any 2 particles, let's say we fix this particle and this particle, call it particle 1 and particle 2. If we fix and then try to look at the force experienced by these 2 particles relative to each other, U of Rn, how would we do that? We would get that by differentiating with respect to R1. And if you look at this thing, keeping R1, R2 fixed, but averaging, so this big capital thing, the big capital brackets, you have probably seen things like this in quantum mechanics a lot if you have taken it, and we will be dealing with such brackets more and more. So this means that we have kept R1 and R2 fixed, and we average over all others. So this is the mean force experienced between these two particles, and this came out to be equal to kBt d by dr1 d ln g r1 r2. Mostly we are interested in spherically symmetric systems. When you apply these things to your research, you will not be dealing with spherically symmetric systems because those are not that interesting. But here, for the simplicity of math, we will be dealing with spherically symmetric systems where we are mostly interested in R. So there we are interested in things such as kBt, d by dr, ln g of R, because all that matters is the relative distance. And there we can say that the average force, this is capital U, because this is the full n-body potential by dr. Average force between two particles as a function of their distance, moving all other particles and averaging over them. The reason why this average is a slightly funky average is because every configuration comes with its own e to the power minus beta u r n weight. That's what it makes it hard to calculate. So if you had a configuration where, let's say you are interested in these two particles and the other particles, let's say they are interacting to some generic potential, I don't know what's the form. You would imagine that such a configuration where the other particles are scattered throughout the box is probably going to be more likely than a configuration where these two particles are still fixed, they are kept over here, but the other particles are all connected in a corner. So you can kind of see that the configuration on the left, A, will have higher weight than the configuration on the right, B. What does that mean? It means that e to the power minus beta u of Rn in configuration A will be a much larger number than e to the power minus beta u Rn in configuration B. So that's the weight that we have to take into account. Weights are a funny thing. If you are doing an experiment, you are sampling things as per that weight. It means that if this number is 1000 and if this number is 1, it means that if you run an experiment, you are likely to observe the system in the configuration A 1000 times more than the configuration B. So that's kind of nice in an experiment. In a simulation, it becomes a bit complicated. So that's what we have, but let's try to get some more intuition into what this equation looks like. So you saw in the last pop quiz that G of R versus R for an ideal gas looks something like this, right? It was just 1. That was the idea, or some constant. So using this relation, what can we say about the average force experienced between two ideal gas particles as a function of R? Let's call this F, because we will be using this again and again in the next few minutes. So for an ideal gas, what can we say about the force as a function of R? What do you think, Jess? You can unmute yourself.
Yeah, I'm honestly not sure.
Well, let's try to think through it. We are saying that the force is equal to the derivative of log of G of R. Okay?
Mm-hmm.
And here I plotted the G of R for an ideal gas, and that's a constant. So if G of R is a constant, log of G of R will also be a constant, right? Mm-hmm. So once we take its derivative, what's that going to look like?
It'd just be 1/1.
It's a constant. What's the derivative of a constant?
Oh, the derivative. I thought it was derivative of ln of G.
But same thing. If G of R is a constant, then ln of G of R, you're right that it will be equal to 0, but more importantly, it will be a constant, right?
Yeah.
So d ln gr by dr is going to be 0. So this is just showing the notion that we would have expected anyway, that the force acting between two ideal gas particles is going to be 0. That's all it's telling you, right? So that's the point. So that's why I wanted to go through this equation, because it looks kind of complicated, but it's really simple. Okay, good, thanks, Jess. So now let's look at something a bit more interesting. Let's look at what we call as a Hart sphere. Hart spheres mean that u of r between two particles, small r, is going to be, so you have spheres instead of the ideal gas. It's similar to an ideal gas. The only difference you have is that you have given a radius sigma to the ideal gas particles. So now it will look like u of r is equal to infinity if r less than sigma, and u of r is equal to 0 if r more than sigma, or more than equal to sigma. Let's not worry about continuity here. It's a discontinuous function. So what should g of r look like for such a potential? I just saw Kevin joined in, so I'm going to ask Kevin. Where's Kevin? Kevin, you there?
Yeah.
Oh, good. Help me, Kevin. What's g of r versus r going to look like? Huh?
I don't know if I can right now.
You cannot?
No.
You have to think through it. Okay, who wants to help me then? It's a homework problem, so I'm helping you guys.
So if it's less than sigma, it should be 0 because it can't exist there.
Uh-huh.
And then if it's greater, if we're treating it like an ideal gas, then it should be just 1.
Yeah, exactly. So what Pawan, this is Pawan, right?
Yeah, it was.
So what Pawan just said is that if r is more than equal to sigma, then if you just ignore this part, then it is like an ideal gas, right? There is no interaction, so it should look like 1. But r less than sigma, it cannot exist, so it should look like 0. So this is, so I helped you with your homework problem, so that's good. You get more points now, for sure. Then force, what can we say about the force using this relation that we wrote over here? I will write it down again for your help. That average force is equal to kBT d by dr ln g of r. Who wants to help me?
Would it just be a sharp spike where r equals sigma,
Yeah,
and
exactly.
then 0 everywhere else?
Exactly. It will be a spike over here, and then 0. But that also makes sense, right? All you are saying is that the hard spheres don't experience each other. There is no force between them. If r is less than sigma, or if r is more than sigma, there is no force, right? Otherwise, there is a sharp delta function.
I have a quick question, just like a terminology. This is Luke. I'd heard before people talking about just like modeling particles as like as sticky particles is like a word that's used. Is that an interchangeable term for saying you're modeling things with a hard sphere versus as sticky particles, or like is that a more physical kind of?
I'm not 100% sure. I mean, the people who model hard spheres and all, they have their own industry and they come up with more and more complicated things. I don't know what exactly the sticky particle. You can introduce, I mean, not to sound demeaning, but you can introduce lots and lots of variety on this U of R. So I don't know what exactly.
Okay.
But let's go to something which is.
I had a quick question.
Go ahead.
So with the previous graph, shouldn't it be infinity for all values less than sigma? Since it's not only at sigma, it's anything closer to it as well, right?
No, why would it be? You are looking at derivative. This is a constant.
Ah, that's right.
This is a constant.
Right. Never mind.
Yeah. So now let's look at a crystal. A typical G of R for a crystal is something like it's 0, there is a peak, then there is some other peak. These correspond to, let's say, sigma 1, sigma 2, sigma 3. So they correspond to the first neighbor distance, the second neighbor distance, the third neighbor distance. And again, in between, the G of R is constant. So the force will be 0 and you will have delta function peaks at wherever these peaks are. So, and here it's going to be a bit more interesting, because in this one, the G of R climbed up and then stayed constant, right? Here the G of R goes up and then goes down. So anyone wants to help me? How will the average force look over here? And you can use your intuition. Let's see, I don't want the same people answering again and again, because, so is Sai there? Sai is not there. Raquel, can you help me?
Hi.
Yes, she unmuted, wonderful.
Before that,
Before sigma 1, how should it look like?
before in the past graph, I'm just gonna make a question.
Say again?
If you go to the other graphs in the other page, page 2,
Yeah.
I just wanted to make a question. I don't know if I understand why you, in the G of R graph, why did you connect the 0 with the 1? Wasn't just supposed to be like one line at 0 and then the other line of 1 without this vertical line?
Oh, you're talking about this?
Yes.
Yeah, see. So Raquel is very smart. So when you guys all become professors or scientists and you give a seminar and someone asks you a question, the best strategy is to ask them a question back, you know? So that's what she did to me. Wonderful. No, you're right. This is only for your visual help.
And then okay, so if there is
Very
no
different.
thing there,
Continuous.
why in the F of R graph we have this spike?
So if we really zoomed in this graph, I think we are getting into mathematical domain. What will happen? So my first answer to your question would be that realizing exact hard spheres in life is going to be very, very hard, right? It's going to be difficult. This won't be an infinite. This will probably be some very large function, right?
Mm-hmm.
So when it is a very large function, this thing won't be exactly a dotted line. You will have some sort of a finite range over which it rises. That's the main reason why you will be able to not see anything like this. But more importantly, this is a mathematical discontinuity. So you have sigma, and for any r tending to sigma minus epsilon, and any r tending to sigma plus epsilon, for epsilon more than 0, you will find a large enough value. So I think it's a mathematical ill behavior. So if you really want to be precise over here, you should plot something which looks like this, you know.
Okay, but it's just because by just looking at the equation for F, I would say everything was just 0. If I look at what G of R is in the previous graph.
Yeah, so what you are saying is that this thing might be very hard to observe.
Yeah.
And it actually might just look like 0.
Okay.
That's what you're saying, right?
Yes.
But what I'm saying is that it will be 0 indeed everywhere, but you will have a discontinuity at sigma. Let's think of it that way, right? So the force is continuous if R is more than sigma. The force is continuous if R is less than sigma. It happens to be 0. But at R is equal to sigma, it's going to be suddenly two things are banging into each other, and it's going to be very tight right there, and it's not a good thing. Good? Does that help you?
Okay.
Now you help me and tell me how it's going to look like for a crystal.
Okay, so in the part that is 0 is going to be 0.
So let me draw it. It's 0, and then?
And then there is a spike, which then it's going to be
Spike.
yes, like I think the same kind of thing for the other two.
So, and should this spike be symmetric, or should there be a negative sign?
Okay, so the derivative of going up is positive, but then the derivative of the down part is negative. So it should go all the way down.
Yeah, so this is something I'm going to, I want all of you to think about this one because it's interesting. So I'm going to amend this to your homework 4, and I will be adding this as, I will make it a 110-point homework. And I will be adding this as last problem is to plot F using this relation, F is equal to KBT d by dr ln gr for a crystal. Okay? And I want you to draw this. It's more interesting than I thought when I just drew it here. So I want you to think about it in the homework. Good. So we will leave that. But you can see interesting things might happen because it might be negative over here. What does that mean? What's going to happen in the middle? So it's worth thinking about. And the physics here is, thanks Raquel, you can, you already unmuted yourself, so that's wonderful. So the point here is that if you have a crystal and you are displacing this atom away from its first neighbor distance, then it would like to come back in this direction. The R would like to decrease. And if you're displacing it in this direction, then the R would like to increase. And that's what your plot should agree with. So I will add it as a final problem in homework 4, and I will update it in the spreadsheet. Good. So hopefully this gave you a bit of intuition into this equation. Maybe it confused you even more. Both things are okay. Confusion is a key part to understanding things better. It's neither necessary nor sufficient, but it helps. So, and in complicated systems, when you have a biomolecule, this is my drawing of a protein, and you have a drug sitting inside the biomolecule, and then thinking about the average force that is acting between a particle on a certain atom in the drug and a certain part of the protein, these things can be very useful. And you can do some scattering experiment on the system, and then you can talk about what is the force between them. So that's one use for G of R. Today, what we are going to talk, that was page 3, let's call it page 4. And let's talk about, we are going to talk our discussion of how to get thermodynamic properties from G of R. So to do this, we are going to assume an interaction model. We will assume, and it's possible to do it in a very general case. The math becomes harder, otherwise the concepts are similar. We will assume an interaction model for the potential energy, for the n particle potential energy. So remember, this is full n particle energy. That's going to be a complicated function in general. So we are going to assume a model where this is given by looking at pairs of atoms I and J. And we are talking about pairs. So I cannot be the same as J. It has to be different. And a small u that accounts for the distance between these two particles. So the potential energy, so this is a function of, this thing is a function of n variables, but what we are saying, it's actually a piecewise sum of different functions of two variables. Furthermore, how it depends on the two variables, it's very simple, because you could also have theta and phi and all these complicated things over here. So typically this small u of r, you saw an example for small u of r already in the last couple of slides. Heart sphere is an example of small u of r, where you have infinity. And again, before Raquel gets angry, this is just for your convenience. It's just to join the two things. It's 0 and an infinity. So this is an example of U of R, the Hart sphere interaction. A more realistic example is something called Leonard-Jones interaction, where Leonard and Jones were not two people. It was the same guy's name, his last name, I think. So here, a more realistic example is when this U of R goes to infinity in a gradual manner and has a minimum, and then it gradually goes to 0. So a typical form for such a potential is A by R to the power 12 minus B by R to the power 6. That tends to have such a behavior. There are interesting reasons for why did we take this power 12 and power 6. It really accounts for the van der Waals interaction. Most of the times van der Waals interaction happen in chemistry, they are due to dipole moments talking to each other. And if you have done your electrodynamics from Griffiths and all those books, then you might remember that the potential energy between two dipoles interacting with each other, it's not like Coulomb interaction. It doesn't go like 1 over r square. It goes something more complicated. So there are reasons for taking this R2 bar 12 and R2 bar 6 term. We are not interested in where these terms come from. What we are interested in is, this is one example. There could be many others for this thing, but the generic thing we are going to look at is that the n variable potential is made up as a piecewise sum of functions of two variables, specifically the distance between atoms, and we don't consider the angle or things like that. So, so what we want to do now, so this is called pair approximation. So we are going to work within the pair approximation. You could have a triplet approximation and have a lot of type 2 or type 3 fun with it. Let's work with the pair interaction. So now we want to talk about thermodynamic properties. Let's start with the total energy of the system. So total energy of the system will be given by average sum of average kinetic energy and sum of average potential energy, right? Kinetic energy is a function of all momentum coordinates. Potential energy is a function of all position coordinates. If all particles' momentums are separate from each other, why is that true? Because the Hamiltonian itself, the momentum coordinates are separate from each other. So this thing is simply going to be n, capital N, multiplied by average momentums, average of p square over 2m. This over here, and I should be numbering equations again, let's call this as, I don't know, what equation did I stop at? 13. I see it 13, 14, 15, 15. Good. So we can go to equation number 16. Let's call this as equation number 16. So if you use equation 16 here, you can write down the sum that you had, which is I more than j equal to 1 capital N small u modulus of Ri minus Rj. We know the value of this thing. That is simply capital N. Who wants to help me? What should be the value of average p square over 2m? Where is Suhas? Suhas, any guesses for me?
I had this was coming to me.
It should be related to the average temperature, right? Equipartition, that's your hint.
Right.
Is it gas constant?
It's a similar thing. Instead of gas constant, you will have Boltzmann constant, 3 over 2.
Right.
Why did this happen? Because p square over 2m for one particle is px square over 2m plus py square over 2m plus pz square over 2m. And we know that equipartition says that on an average, each of them is half kT. So total is 3 half kT, okay? Thanks for asking. So, and how about this one? So this is a bit interesting. We are saying that it is made up of pair interactions, but note that we are saying that U is same for every pair. Our system is made up of lots of different pairs of atoms, right? So we are saying that the interaction between them is some small u, interaction between this is some small u, between this is some small u, even this is some small u. All of them are some small u. It's not a harmonic spring, it's something more complicated possibly, but they all have the same interaction potential. So now, if that is true, then just like we had a capital N over here, we can do something similar over here. And that number here will be n choose 2, or n multiplied by n minus 1 divided by 2, right? Those are the number of pairs we can form. And each of them will have its own average interaction, small u, R12. Instead of R12, you could have written R8, 9, R14, 15, doesn't matter. What matters is that you're saying is any pair gives the same average energy, and there are n multiplied by n minus 1 divided by 2 pairs. That's the idea here. with the very number of separate pairs. The 2 accounts for the overcounting. So in order to calculate the total energy, we really have to deal with this term over here. So let's do that, and let's look at it carefully. So what we have over here is let's write down the meaning of this average in terms of all the machinery we have now. So if you remember in the first lecture that we did back in the days when we could meet in person, we talked about that statistical mechanics is all about calculating averages, calculating about second moments, third moments, things like that. So what does it mean to calculate such an average? What it means, any average is looking at some property, multiplying by the probability of that property being observed, and then normalizing the probability, right? That's the type of thing we are doing. We go to space coordinates or momentum coordinates if needed, and we average over all that. When we are talking about average of u r12, clearly we don't need to worry about momentum coordinates. There is no momentum coordinate here. So we need to average over only potential coordinates. What are those potential coordinates? The thing to keep in mind here is that these coordinates will be all n particles. You are not excluding r1 and r2. This includes all n, my includes look like, includes all n particles. What is the observable over here? Observable is our small potential energy u of r12. What is the probability of observing such a configuration? That is the Boltzmann probability, exp of minus beta capital U of Rn. And now we have to normalize it. How do we normalize it? And I'm forgetting the n minus 1 by 2 thing that we had that needs to stay on the side. When we normalize it, we keep the same thing, but instead of having this thing disappears. So here we just have exp of minus beta capital U r to the power n. That's where we are at. Let's call this as equation 17. Let's call this as equation 18. So I'm going to write down equation 18 again because it's so important, and I'm going to write down without looking at anything so you can see that it is not that hard. What we did was to say that n minus 1 by 2 times average of small u of r12 is given by drn u of r12 e to the power minus beta capital U of Rn divided by the normalization factor Rn e to the power minus beta U Rn. And this I can bring it inside. So if this type of math looks complicated to you, over the course of next few classes, you will become more comfortable with this. Some of you will become very comfortable, some of you will become somewhat comfortable, but you will become more comfortable. And it's really not that hard. In fact, in my group, I can say with a guarantee that I think this is an equation we use every day in my group. This is all we do basically to calculate equations very similar to this. And we do it in a variety of fun ways. So yeah, go ahead.
This is Luke. I have a quick question. So you're saying the potential of the interaction between like R1 R2 is it? So we integrate it over all. Do we integrate it over the whole space? Because like I guess one way I was trying to think of that is that this little u is technically is a function of everything, but it only picks out 2, and so. Because when you average it, since it's a function of like all n, you do the...
Yeah, so the thing is this, yeah, good point. So this little u is a function of only R12. But observing the system at a given R12, it's not just going to depend only on that 1 and 2. that's going to depend on everything else. And this is common sense, right? Like in an ideal world, Luke and I could be the best of friends. But then we have to take into account that Luke has a co-advisor and Luke has to take classes and Luke has to do research, and I expect him to be very prolific in publications. You know, this is the environment that you take into account. So that's a subtle fact, but it's very important. Even though the potential is just computed between these two, that's why it depends on these two. But to calculate the probability of this configuration, you have to take into account there are other things sitting on side. You know, there is coronavirus, which decides how you and I interact with each other. So that's why the probability is a function of everything else. Okay, that's a philosophical answer to your question. But let's write it down.
That's helpful.
Huh?
Then, no, that's helpful.
I'm still confused by this.
Who is this and who is confused?
Ben.
Ben is confused. Tell me, Ben, why are you confused?
So the little u is a function only of R1 and R2.
Yeah.
Yeah, these two particles.
Yeah.
Or their relative separation, right?
Yeah. Yeah.
So, and then I just don't see why don't the all the other coordinates just integrate out?
They will, they will, in the next step, that's what we are going to do. But the thing you need to keep in mind here is that observing the system at a certain, observing any two particles at a certain separation is going to be a function of how everything else around them is behaving. Because these two particles are interacting with everything else also, right? If they were not interacting with everything else, then nothing would exist and it would be a really simple integral.
Well, I'm thinking just mathematically. So you have like integral dr1, dr2 cubed, whatever, dot, dot, dot.
Yeah.
drn cubed.
Yeah.
And then you have u of r1 and r2.
Yeah.
And then you have e, a product of all these exponentials, e to the minus beta.
Yeah.
Wait, no, you have e to the minus beta. I guess, u of rn could be very complicated, right?
Yeah.
It does. Okay, u of rn doesn't necessarily have to be separable.
No. Well, we are assuming pairwise interaction here.
Okay.
So let's yeah, I will be expanding this equation, so that will help. But the thing to, again, let's look at this equation again. All this is saying us is that any property f will be given by integral dr capital N f e to the power minus beta u r capital N by dr capital N e to the power minus beta u r capital N.
Right. These are just like, like we
no one has a problem with this equation, right? This is just a canonical ensemble. Here, f could be a function of r1, r2,
right.
Capital N. It could be a function of r5, r6, and r7. I am saying f is here a function of r1 and r2.
Right.
More specifically, f is small u of r1 minus r2. That's what we did.
Well, it's kind of like we're implicitly doing this with momentum here because
in a way, yeah.
It's like you don't even think about it, but like, when you do the probability distribution, there's not momentum in there because we know it's gonna, this is more complicated than that, but like.
But let me write down the next form and then you will see that it is not that hard. This is the intuition for this equation, but now let's actually try to calculate it. So now what we can do is to take the equation. So this is an aside just to show where it comes from. This is just calculating an average. So now we can take this capital Rn and break it down. What is the capital Rn? That is R1, R2, R3, all the way up till R subscript capital Rn, U of R12, e to the power minus beta capital U of Rn, divided by, in the bottom, we could do the same thing, R1, R2, Rn, but there is no small u here, it's simply e to the power minus beta U of Rn, and we are continuing to dangle this n minus 1 by 2, it will play a role soon. Now think about it, that this can be written as integral dr1, integral dr2, and we bring out our small u of r12 out here, and then do all the other integrals, okay? dr3, dr4, drn, e to the power minus beta capital U of Rn. Denominator, I'm not going to do anything, so I will just rewrite in the form that I had it earlier, minus beta capital U of Rn. And now I'm going to do one trick, is to take this thing over here and write it as a half up front and an n minus 1 over here. Now we are getting somewhere. And if you have been paying attention to what we have been doing, then this thing is something we have seen before. Notice it's not multiplied by this. This thing, the blue bracket is inside the integral. So what we have over here is half dr1 dr2 integral of u r12, and this integral is calculated over u r12 multiplied by something else. Does anyone see what is this something else? Where have we seen it before?
Like G of R or something? Is
Is
it
it
G?
P or is it rho?
Rho, okay.
It's rho. Remember, P, it would have been P of R if we didn't have this n minus 1. It was the reduced distribution function which corrected that we care for any two particles. This is rho 2 of R1, R2. Suddenly the math became simpler. And there we are. This is the wonderful relation that I had showed you when, remember, I had tried to I had in this class, I'm looking at last class's notes. Where is it? We had wrote a property like this: for any observable dr g of r multiplied by rho. Yeah, let's not get confused there. Let's look at this. So this is what we have. And why did this happen? Because this is, per definition, this is how we define the reduced distribution function. If we did not have this n minus 1, then this would have been P2 of R1, R2, right? But we do have an n minus 1. So this is P2 of R1, R2 multiplied by n into n minus 1. And that is rho 2. That's what we used over here. So we have our most important relation, and now we can write it down. What did I call this page number? This is 5, 6. This is page number 7.
And so this like dependence on all the other particles, that's coming in because we have terms like R1 minus R3, little u of R1 minus.
Yeah, exactly. It's not a beautiful world in which particle 1 and particle 2 only talk to each other. They have to take into account the role of the solvent, and that's why it's so complicated. So this is powerful stuff because you are really seeing how to deal with everything else in here. So now we have our important equation, which says that the average energy of a n particle many body system, n particle many body system made of pairwise interactions. That's the assumption we had over here. Made of pairwise interactions is equal to half d of R1, d of R2, small u of R12, rho 2 of R1, R2. And this equation looks complicated, but if you keep into mind that for spherically symmetric molecules, rho 2 of R1, R2 is nothing but rho square of GR12, right? So therefore, let's number this equation 18, let's call this 19. So therefore, capital U of Rn for spherically symmetric molecules is going to be half dr1. And now we can look at the relative distance from R1 to R2, some vector like this. Small u R12 multiplied by rho square G of R12, where is the distance between R1 and R2. Integral of, so what have we done over here? This thing is completely independent of the first part. The first part is simply half over volume of the system. The rho square can be brought out, so it becomes rho square by 2 multiplied by volume. So we have taken care of this into this as well. And now we can do a change of, just rename the variables. Instead of calling dr12, we will call it dr. And we have a g of r, and we have a small u of r. This is in turn rho v by 2 d of r, and I'm just going to use r. Should I, or should I keep the vector? Let's keep the vector for now. D of r, rho g of r, small u of r. One rho has been brought inside. What is rho multiplied by v? That's the number, because rho per construction is n by v. So this is n by 2 d of r, rho g of r, u of r. And this relation is not very unintuitive if you take into account the nice property that we derived using Bayes' theorem for rho g of r. It is the conditional probability. So you are taking one atom sitting somewhere. You are looking at having another atom at a distance r from it somewhere else. The probability of this event happening is given by rho g of r. The total number of such pairs would be n, something like n, and you divide by, you could do this for n atoms, so you multiply by n, but then you would be overcounting, so you divide by 2, and you get n by 2. So it's an intuitive and a beautiful relation. Although beauty depends on the observer. So now we can write down the full thing, the average E. So Haas had helped us with the momentum part, that was 3 by 2 nkt, plus we have this relation that we just derived, n by 2 rho. And now we can switch to spherical coordinates and use our nice g of r. So these phi and psi angle of spherical coordinates integrate out to give us 4 pi r square, and we get g of r, small u of r. Therefore, average, mostly energy is an extensive quantity, right? So we are mostly interested in average energy per particle. That's going to be 3 by 2 kT. That's the relation we expect for an ideal gas. Every degree of freedom, it's the momentum thing. But everything else contributes a half rho, the interaction contributes a half rho dr 4 pi r square g of r, small u of r. So using the g of r, you can derive the total energy as a function of density. If you were an ideal gas, then rho would tend to 0, and we would be left with this. So it meets common sense, or physical chemistry type common sense. So for an ideal gas, we would recover pressure is equal to rho kT. But now the question we want to ask is, for non-ideal interactions where small u is not equal to 0, how does pressure depend on rho? And we have seen examples of this in the past. If you have taken any Chem, one example is van der Waals interaction, where you take into account that particles have a finite size. there is also virial expansion, and we'll be looking at things like this. And what we are going to do now on, and I'm going to stop a bit early today because here the math gets really clunky. And I think I have subjected enough math on you. I want you to take the time, instead of us pushing through, I want you to take the time and go through what we did and see if you understand it completely. What we are going to do is to calculate the pressure using our wonderful relation KT is equal to partial ln Q by partial volume at constant number and temperature. And we know how to calculate partition function. We have been doing it all through. That's how we calculated averages. The math gets a bit clunky. And so next class, what I'm going to do, where is my Chandler's book, is to, Chandler gives this as exercise problem. He doesn't even go through the details. He was a mean guy. May he rest in peace. But this is Chandler exercise 7.11 that we are going to do in next class. And I will write down the result that we are going to prove, or the problem. It is that show that when U of Rn is paired decomposable, which is what we are working with, then the pressure is given by beta times pressure by rho is equal to 1 minus, again, beta times density by 6 integral d of r g of r du by dr. This is the relation we are going to derive. This equation is called virial theorem equation of state. So if you remember your PChem, in PChem, when we go to non-ideal interaction, the first thing in PChem, the first way to look at non-ideal interaction is the van der Waals equation of state. The second one is the virial equation of state. But when you look at virial equation of state in PKM, we just have a coefficient that we introduce. We call it the virial coefficient. We don't talk about what is that coefficient. Here you have an actual perspective into what is that virial coefficient, what is it arising from. And you can see how it has all the nice properties. Density goes to 0, this term disappears, and you have beta p by rho is equal to 1, ideal equation. U is a constant, du by dr goes to 0. Again, you recover ideal gas equation. So it reduces to all these things. So this is Chandler's problem 7.11. It has a star. This is what we are going to solve. If you want to go and solve it for your own personal satisfaction, please do it. The next class, it will be very easy. And when I get stuck somewhere, you can come and help me. That's what we are going to do. After this, we will derive van der Waals equation of state from yet another perspective. But the key thing we did in today's class, let's recap, and then we can stop in less than 5 minutes, is to try to develop a bit of intuition for this formula that force is equal to d by dr of ln g of r. We try to look at how this looks like for a hard sphere, for an ideal gas, and I'm going to add one more problem to the homework, which I released this morning. So I have to tell Sai because one student is missing in the class. Who here is friends with Sai? Turash, you know Sai well, right?
Yeah.
Could you please communicate to him that there is one more problem on homework 4?
Yeah, I'll tell him.
Okay, thanks. So, and for Crystal, I want you to look at this carefully and think how it would look like. Then we continued our investigation of how to get average thermodynamic properties from G of R. We looked at pairwise interactions, such as Leonard-Jones. There we said the total energy is made of kinetic energy plus potential energy. Kinetic energy is just equipartition. Potential energy is a sum of pairwise interactions. And the next few things are the type of things that spend some time going through it until it becomes obvious. When it becomes obvious, you will be like, wow, we did not really cover much in this lecture. It was so easy. But until it becomes obvious, you will be like, oh, we covered too much in this lecture. This was too complicated. So go and think over this. This operation, what we did over here, is to calculate a thermodynamic average. So I will put this in red. We did not really do anything funky. We just calculated a thermodynamic average using our Boltzmann using the property for a canonical ensemble. It's just that the math looks a bit more complicated because now we are in interacting systems, n particle systems. We cannot just write down the partition function for one particle and take to the power n, right? That's why life before coronavirus, at least in this class, was so easy, because you had one particle, take the partition function, take to the power n. But now you can't do that. You have to really deal with everything else. And you can see an example of why it became complicated. But then we went through it. We introduced our good friend rho 2 of R1, R2, the reduced distribution function, and we got this wonderful relation that gives us how the energy depends on the G of R. What we are going to do next is to solve Chandler's 7.11 and to derive virial equation theorem of state. Again, no surprise, you have G of R showing over there. We will derive equation of states from some other perspective. And then I will be talking about something called statistical mechanics perturbation theory, which I enjoy a lot for a variety of reasons. The guy who really introduced it was Zwanzig, who used to be a professor in IPST and chemistry until early 80s and then moved to NIH. And Zwanzig introduced this in early 1950s or something for his PhD work. And we will be talking about statistical mechanics perturbation theory, which is extremely important in a variety of fields, from material science to drug design to everything, and we will be going through that. Once we finish this, we will be talking about phase transitions. And there you will see why Chandler's book has this particular cover. This is something for an Ising model, and we will be talking about Ising models. We will be talking about wonderful things. For example, we will show that a 1D material cannot have any phase transitions. In order to have phase transitions, you must have at least 2 dimensions. And this stuff, I think, is really beautiful. So we will covering all of this in the remaining part of the semester. At some point, we will have a second midterm. I mean, at this point, it's guaranteed to be a take home. I mean, I cannot give you in-class midterm. I could do things like, they have these apps where it watches whether you're opening some other browser or this or that. You guys are all, except one of you, you're all PhD student, and the one who is not a PhD student is also kind of a responsible person. So I trust you. I will give you an exam again with 7-day window to finish it, and you can go and think through things. So any questions about today's class? Okay, so otherwise our office hours will be Monday and Thursday, I think. It was Monday and Thursday, right? So Monday and Thursday, 3 to 3:30 p.m. both days, and 3 to 3:30. You can come to both if you want. You can come to neither. It's up to you. Okay, and I will post this material online in a few minutes. And the homework is up. I will be uploading a 6th problem. It will be a bonus problem. So the homework will be 100 points, but I will make it for 110 now, so you can score more than 100. Okay, so see you on Thursday. With the coronavirus, I don't know what is weekend, which day is what. Imagine you guys are in a similar spot. Okay, see you, bye.